Good afternoon. The honeymoon is over. Today we are on marathon. So bless yourselves. So yesterday we looked at the spherical symmetry, and according to spherical symmetry, so yesterday we were able to look at the spherical symmetry, and we used the natural example of a tumor, whereby we ended up having our E being the same as rho naught over 3 epsilon naught r cubed over r squared for when we are outside the tumor. We got rho naught over 3 epsilon naught r when we were inside the tumor. And from this expression, we were able to get the relationship between the radius or the distance from the center of the distribution to the Gaussian surface we are drawing, such that if we have this as the electric field intensity drawn against the distance or the radius of the spherical surface drawn symmetrically along the distribution, which was a sphere, then we say that inside the sphere, or inside this spherical distribution, we would get the linear proportionality, and as we reach the surface of the sphere, then we start getting the electric field intensity reducing inversely proportional to the square of the radius of this surface. So we got this forming an asymptote, almost joining the r-axis. This was our 1 over r squared. And it's on this point, and then we say that we look at the second one, which was the cylindrical symmetry. And the cylindrical symmetry, we say that draw a Gaussian surface, which is a cylinder, sharing an axis with our cylinder, and this axis can. So we draw a cylinder, and this cylinder will be coaxial, we say, sharing an axis with the original cylinder. But there are a couple of things we need to know about this kind of symmetry. When we were looking at a sphere, yesterday when we were looking at a sphere, we said we draw another sphere sharing the center. That is by drawing a concentric sphere. And as you can see, when you draw a sphere, you have this being the center. We can draw the equatorial plane, like if you slice an orange into two, you'll be having one piece. If we drew our axis along this part, we would have our z along the vertical. We would have the x, and then we would have our y. So when we talk of any point on this sphere, it means that if you were to get any line along the radius within the sphere, and then you come up to a given point on the surface of the sphere, any point at this point here, you have the elemental surface area, which we call the S, being along the radius, okay? And so is the electric field intensity. We also have our electric field intensity along the same radius, because we say that the electric field intensity is acting outwardly, radially outward, radially outward of the sphere. So we eventually got our expression as if actually this charge was concentrated at the center. So, if we follow the Gauss's law, integral over the closed surface E dot S, it means that this is the dot product of the electric field density and the surface element along the radius. And when we dot these two, because the surface, the elemental surface vector is along the radius, so is the electric field density. The dot product is the product of the magnitudes of these two quantities. And when we dot them up, the magnitudes, we multiply by the cosine of the angle between them. And what is the angle? 0 degrees. So that means that we eventually get this one reducing to 1, and that's why we were getting an E, nu, the total surface area, which we were getting as a 4 pi r squared on this other side. That's how it came about. Now, when we graduate from this sphere, of course, when you draw the, normally this is an R, any distance from the center to the sphere, which is the radius, and then you take the shadow to the equatorial region, and that one, casts formulates along the equatorial region. You get your phi, and then the angle this radius makes, depending on where you started. If you start from Z, if you go to Mwere by evening, I will activate the GIF or the animation that shows you how the radius covers the angle theta, which is theta here, which you covered in your mathematical physics, whereas the phi, sometimes you find being drawn like that, will be the angle swept across the equatorial region, whereas R sort of is the constant because you are always at the surface of the sphere. But if you now get this sphere bulging out, like if you were to blow a balloon, which is spherical, not these ones which are a bit artistic for parties, you blow it when there's a small balloon, it keeps being big, so the area is increasing. So that's why you find that when we are measuring the R can range from when you have no radius, if you add a point charge, and then your phi will be increasing according to up to 2 pi, because you are taking the equatorial, and then when you look at the theta you think will go from where to where? 0 to pi. Because actually you start, if you were to slice the upper part by slicing the tomato longitudinally, or this mean orange longitudinally, then you would have this angle being able to sweep across these field lines. If it goes the other side, it will be cutting from the same field lines on the other side of the longitudinal interface. So now that we are acquainted with the spherical, how the spherical configuration is, then we look at the cylindrical symmetry. We now chose a cylindrical distribution of charge, whereby, for example, you may have a line like a cable, and this cable is housed in the charge. For example, we may have a cable with a positive charge, and this positive charge is leading to a field around this cable. for example, coaxial cable of a TV area. So, if we now take this kind of example, we shall draw our Gaussian surface. And our Gaussian surface can be as much as this. We can give it a length L and radius small r. Now let's look at where the symmetry is. So we said in order to apply Gauss's law, we must make sure that the symmetry is well cared for. Now if we look at the E produced just by looking at the edge, where we can easily see the geometry. So if we have E coming outwardly, you got a lot of them going this way, we can draw another one here. So I'm looking at the end of the, I need to borrow a paper, a piece of paper. These days I'm becoming a environmental friendly, so I didn't carry my papers. The end of the cylinder. So this is my end of the cylinder. And if you look at the center, where our copper wire is, which is producing the field, that's where I'm bringing out the idea of that the field lines are all through getting, perpendicular to this surface. So we are having the electric field lines perpendicular to the surface and running out radial, or running radial outward. Okay, but then that means there is symmetry around. So how about, or what happens to this other side? So for any point, any part of the surface, if I chopped off a little bit of this paper, like I, scratch out or cut out what we call the Benon surface area. That Benon surface area would be along the radius, so we would be having that ds coming outward along the radius, and so is our electric field intensity. But let's look at the what is happening either on this other side of the part we are considering, the surface area, which is the cross-sectional area of this part here. It means that if we look at this as the area which is contributing the electric field intensity, this is our electric field intensity E, which is radial. Okay? But the area which it is being associated with, we draw our ds, and if you remember, ds was equivalent to m curve and a Benon surface area, meaning that we take this ds as being normal to the surface. So if we consider this cross-sectional area, our ds will be perpendicular to the cross-sectional area. If we cross it with our E, definitely the first thing I say that is along here is very wrong. The E is radially outward. So if we take this to be, not taking them to be, but of course they are perpendicular to each other. Hence, we cannot apply the Gauss's law either on this side or the other side. And that's why when we say that we integrate the E ds, this would culminate into 0, because E and ds are perpendicular. So the dot product would net to be, or would result into 0. I still need it, but I'll keep it clean, don't worry. Any questions upon why for a cylinder we won't consider this either side, because they run to 0. So we only left with this other part. So To our today's needs, I bought that machine expensively to also act as a clock. So we'll get it, bring it here. I want to make sure I see what time is moving. A watch is the one they put along your wrist. A clock is the one which is, you can't fix it on your... No problems now. There is no problem here. After all, I'm just repeating what you studied very well in mathematical physics and in mathematics. So we choose for a Gaussian surface. We choose for a Gaussian surface a cylindrical surface, coaxial, sharing the same axis with the charge distribution. And we can take an example of such a scenario whereby we take a long cylinder, carries a charge density which is proportional to the distance from the axis. And this variation is rho is equal to Kr for some constant K. After knowing all this, or having such a cylinder, we yet to find the electric field density, E inside and outside the cylinder. So we got our charge distribution. The first case, which is inside, we take the case of our cylinder. It is an infinite cylinder, or a very long cylinder, but I'll just draw a section of it. I can't draw anything infinite on the ball. And then I got the axis of this cylinder. So I can also make this one solid. So this is the axis of the cylinder. So I draw a Gaussian surface mimicking the cylinder or the cylindrical distribution of charge. So I'm drawing this cylinder inside, that, and then we have the electric field coming out radially. There's another one here, another one here, another one here, another one here, the other side, symmetrically. So if we take this to be L, and let's take the outside to be capital L, the radius of the Gaussian surface is small r, whereas the whole cylinder is having a radius capital R. We are having this one inside being our Gaussian surface. Of course, by symmetry, I've already explained that there is no flux. There is no flux of E through the ends. Remember, flux phi is equal to E dot scalar because of the dot product. And we say that the dot product at the ends is dotting the magnitudes, and the angle between them is 90. You won't get anything. So the flux of E through, of course, you know there is also flux of E, okay? Which is equal to B. Yes, that's why we say flux of E through the ends of the divisions of the cylinder. Let's say of the cylinder. So E is basically radially outward. So we say that E is radially outward. So we got the question now. The question says that the charge density carried by this cylinder is proportional to the radius from the center, which would be the same as rho is equal to kr for any constant r. So applying, now I don't need any more of this. The information has been translated into the diagram on the other side. So now I can apply, we are still under the section of application of Gauss's law. So now I can apply the Gauss's law. So by applying Gauss's law, then I would say that the integral over the closed Gaussian surface S E dot ds would be the same as the total enclosed charge of epsilon r, and the total enclosed charge Q enclosed will be represented by Q enclosed equal to integral over the volume tau rho tau. So we get this as over the volume tau. This is over the surface S, where S is our Gaussian surface. Would be the same as rho d tau. And now we can see about three guys talking. They think they will pass. Right. So I'm going to have to calculate the surface area of this Gaussian, cylindrical Gaussian surface. Now it means that I have the cylinder here. This is our cylinder. If it was a can of a tin of either needle or milk, we've agreed that it covers the bottom and maybe the top, which is the cover, are useless. They are not contributing to our calculation. So the only thing we are left with is the, if I can split our can open, so we remain with this kind of surface. And we shall be interested in how much this surface is affecting the field lines that are going through it. Okay? And that means we remain with this one, which was folded here, is after stretching it, you would have stretched the circumference of the circle of radius r, small, which is the radius of the Gaussian surface. And then I multiply it by the length of the Gaussian cylinder, which is our surface. So I will have our E nu, the circumference, which is 2 pi r, and then I multiply by the length L. That would be the left-hand side of our Gaussian, of our Gauss's law. And this would be equivalent to the 1 over epsilon naught, and then we integrate kr from, so in the book, you'll find that you are integrating from 0 to until when you get r, and then kr the tau. From your mathematical physics, what is the tau equal to in cylindrical coordinates? In the cylindrical coordinates, and which I'm going to explain a little bit, r phi z, what is the tau? The tau is equal to, in the Cartesian, the tau would be the x divided z. If you are having your own z, x, and y. So, what would be the tau equal to in cylindrical coordinates? R, the R, the phi, z. So now I'm comfortable. I'm going to have the course interested, since you all know this. But this is the idea behind, which you also find on Mwere. The animation on Mwere is easy to understand. If we took a cylinder, and after taking this cylinder, we shall have 3 coordinates. I have the z, then I have the x, and I have the. These are the Cartesian coordinates within the cylinder. But we want to know now the cylindrical coordinates. So first of all, we need to know where is R. R is anywhere on the cylinder. And remember, the cylinder starts by being like a stick and bulges up until when it stretches. The R is from the Z to the walls of the cylinder. So if we took this to be R, I'm just drawing it in a nice way, this is our R. If we had a point P, which is R phi Z. Now, this of course will cast a shadow at the bottom here. And this shadow if you took this as a plane, this plane would sweep through to make a cylinder. And that cylinder, that sweeping, is what we call the phi. And the height of this from the center or the origin to where R meets the Z is what we call our Z. So once you understand this kind of description, life becomes very easy. You can now know that actually your Z can only be between what and what? Z can start from the origin until infinity, because you can only go, that's why we are talking of an infinite long cylinder. Like if you have a coaxial cable taking signals within your hotel or also residence, and you are giving out the cable TV, we can consider from one corner of the building to the other corner almost infinity, if you consider the diameter of this coaxial cable. And then this R here would be varied from where to where? Which capital R are you talking about?
That is the radius of the...
Forget about that. We just hear this is actual theory of what cylindrical coordinates are. Just forget about the other one. So R will be moving from where to where? You are from the center, from the Z up to the walls of the cylinder, but naturally, where will you go up to? Okay, so you say infinity, and our phi will be varied from where to where?
From 0 to
0 to? So let's now go to our question, and then now we are supposed to be having here our d tau, and our d tau will be R, dr, d phi, Z. Now in the book, you'll find that you are integrating from 0 to 0, from the 0 to R, here, from 0, from the center of your cylindrical distribution to the surface of the Gaussian surface. Because that's where you are feeling the charge density. Because we scooped that Gaussian surface from the cylinder. You get the point? Now, when you say from 1 to R, in the book you'll find that these R's are prime. Just for the purpose of knowing that if I am differentiating, if I'm integrating from 0 to R, I should be able to differentiate between these R's and this one, but I'm not bothered. Why should I pretend when I know that I'm just doing this for fun? You all know, okay? So, but of course, one thing that you did not make me comfortable with is our Z. Much as the R comes from the origin, but the Z has another Z this side, which is minus. So Z comes from negative infinity to heaven. From hell to heaven. Isn't it? So this would be the same as 1 over epsilon naught. Now I don't have much to say. This would be kr squared, 0 to r. And then I have a dr, a d phi, and a d. So I'll do one at a time, where you just have this being the same as 1 over epsilon naught. This would be k outside. You have r cubed over 3. And you have the 0 to r. You have an phi, 0 to 2 pi, and you have a z minus infinity to infinity. Does that make any sense? Now, but of course, on our expression, our distance here is actually from 0 to small l, because we are finishing the whole of our Gaussian surface which we chose. So we have the z for our example from 0 to l. So almost we got everything. And since we got everything, we can now give the final expression. So this is on the left, we still got our A, 2 pi RL, E naught 2 pi RL. And then we can finally say that we have R cubed over 3 remains. We have 2 pi. We have L. L is go, 2 pi go. 1 R goes, the R remains squared. And we can eventually say that therefore, this implies that our E will be equal to KR squared over 3 epsilon naught. And then we say, therefore, our E would be radially outward, and this would be equal to KR squared divided by 3 epsilon naught R cap. And this is for actually when you have the Gaussian surface taken into the inside. Now, as an exercise, I would like you to find out what would be the electric field intensity. That's why I underlined it somewhere here when I was stating the question. So I want you to get the electric field intensity outside the cylindrical distribution of charge above this one, which we have finished in some sentences. It could be on the previous page or whatever, but I take it as above this one. So also derive or apply Gauss's law to a plane distribution of charge. And this is by formulating or by drawing or utilizing what we call a Gaussian field box. You are now mature enough, I don't have to do everything for you. You should be able to do these things on your own. So, yesterday we said that if we got a bunch of, a charge, and we look at the bunch of electric field lines coming out of it, if we just looked at it, we can basically say that for such a charge, giving out field lines all over, which constitute our E, and when we look at these charges for a unit area, then we talk of the flux. If we try to curl them, if we try to curl them, try to bend them, we would eventually be doing what we call the curl. So imagine you have a potato, And after having this polyhedron, you had put in pins. One pin here, another one, or needles. Let me use needles. Needles sound a little bit fair. And then you try to cut these needles like Benon. You are that muscular, you're that powerful. You eventually find out that you are no longer having. Oh, do you know this plant? I don't know how you call it. I've never seen it here in Uganda. But in the village, whenever I would be looking after goats, there was always one plant that I hated. It grows, and then its flower puts some things which are sticky, too many. So I would put on my nice sweater, you know, which is warm, and these things just get stuck there. So you find you are like moving each of them. I don't know how they call it. They call it Sere. It's a Sere.
No,
Okay, Sere. That Sere thing is very, very funny. So, assuming you got Sere, it's calf root, and then you try now to carve these things there. You eventually will remove Sere, and the thing remains with nothing. So, but assuming that you are not actually removing them, but bending them, carrying them up, so you remain with actually nothing. But we want to make sure that, yes, by eyes, by a mere glance at it or looking at it, yes, we can afford. But you can't just say, by looking at it, I see that this can go to zero. We need actually to look for it, and you know, look for a reason to say actually the power of E is zero. So we shall consider a point charge at the origin for which the electric field intensity was given by 1 over 4 pi epsilon naught, the total charge enclosed by or given out by this unit charge inversely proportional to the square of the distance from the origin, and it will be radially, this electric field intensity will be along the radius of any spherical surface that you will take around this kind of charge distribution. And we can draw it. So we are having our field lines getting out of the discharge Q. If we were to move within these field lines from a point A and, you know, move in our own way without taking keen interest of where linearly we are passing to a point B, which is a distance RB from the origin, and this distance being RF from the origin. And we are having our R, you know, outwards, radially outward, because these field lines on the blackboard in the book would look like as if they are in 2D, but actually they are those which are coming to your eyes as you look at the charge. You are having those which pass by your head, others which pass by your ear. And we can say that, or we can calculate the line integral, and that is by integrating from A to B and following the line A to B of E dl. Of course, if you remember, we said that the tangent, we can get the dl by taking the tangent of the path. So E dot dl would be the same as Q over 4 pi epsilon naught, that is by substituting for E, so it is Q over 4 pi epsilon naught integral from RA to RB. Then we have R roof dot L or R cap divided by R squared. And this was given as the Q over 4 pi epsilon naught RA to RB. Then the R over R. And this would be equal to, if you do the integration, which I trust you do better, this would be over 4 pi epsilon naught in 1 over R from RA to RB. Therefore, we know that this E dot dl is known as the potential V, which is equal to minus Q over 4 pi epsilon naught in 1 over RB minus 1 over RA. And we know that it doesn't matter where you come from. So if you moved from here and went back to this point, it's like if you left me here and I walk outside and I come back and you find me in the same spot, it would be so hard for you to determine the work done I've done. The work I've done. Yes?
If we can break one of it is supposed to be
I think we are integrated in we are having pardon, come again? If I integrate what? Okay, are we okay here?
Yes.
You don't remember this?
There is no problem.
You don't remember this from electricity magnetism? It's not my fault. You don't have to be proud of forgetting what I teach you. Surely, there is no reason why you should be proud of. I don't. Okay, I taught it. I said that R dot dl is equal to R dl. Good. So we are okay here. So when we integrate 1 over R, what do we get? This is a function, this is a differential of the function. So when you do that, what happens? Why am I wasting my time? Work it out. I just want to finish something. So you work out that. I hear natural law. So we don't worry. Just when we are done here, you go through it again. You will find there is a problem. We should be able to work out through it on Thursday. We have enough time, okay? So we notice that the line integral is independent. If you have some quarrels, you ask. I may pause. Still have some few minutes to finish this part. I can pause and listen to you. Where is the trouble? So it should be R squared.
Yes.
Here. Does that solve everything? You are now okay? Yes. Thanks. Yes.
If that one is R squared, but we don't know how we can move from that first expression to the R squared.
You can't know how this one was equal to the other. Okay, but we have our R roof being this party, okay? And we are having, because I've already rubbed the part on the other side, and we are having our from A going to B, okay? And we are getting a tangent, our tangent to the path, being the same as? Yeah. So when these two are dotted together, I don't remember, I don't know whether you remember when we were working on the potential, a vector, is it a dipole moment, you remember? But I don't have time to make you, to remember for you. You have to know that R roof that the L is equal to? Yeah. So find out. Find out that and we should be okay. Okay, so now we get is independent of the path. All it depends on are the endpoints. So that's the integral. That's the integral around a closed path. Around a closed path is therefore 0. If RA is equal to RB, the difference of their fractions, with 1 over x is equal to what? Is called what? Yeah, the difference between the inverses will be 0, such that the integral around the closed path C E that the L will be equal to 0. But this doesn't really give us the insight we got that actually when we look at these three lines and we try to curve them, they will give us 0. So what makes or what gives us the curl of E from this expression as we are trying to come by it actually give us 0. So we get that applying Stokes' theorem, we move from the line E that the L, we introduce the curl, which would be over surface S, and then we have the curl of E, we curl the vector, and then we introduce the surface. If we do that, then we shall have that, of course, where S is the open surface bounded by curve C. C is here, C. But of course we know that above, we said that the integral of E dot S over the curve or along the curve C dot L was equal to. Now, if this is equal to 0, and it also is equal to this, so this is equal to 0. So that implies that our double integral is dx dy for the surface, okay? Curl of E is equal to, ws is equal to 0. These are just instructions, okay? And if they are just instructions, they cannot make anything go to 0. They can make the whole expression to be 0 if what they are acting on is actually there. 0. So we say that it is only the integrand which can be 0. You can't have the instructions getting to 0. Therefore, we say that the curl of E is equal to, and we have successfully gone beyond just a mere, observation to an actual derivation. And coming out with evidence that actually, when you try to bend the electric field lines, you cut out the electric field immensely, and then we can put it in words. This result here should be true for all configurations. So it holds for any electrostatic field. And of course, we know that the electrostatic field is said to be conservative. Just like the gravitational field, the electrostatic field is said to be a conservative field. Now that we have a good idea of the electric field lines and how they act, we can easily by Thursday be able to work on the electric potential.